Welcome to episode 1 of this deep tech series, Quantum Computing for Advanced Reservoir Simulation. In this video, we explore a very exciting question. Can quantum computing transform how we simulate the subsurface? Reservoir simulation is already one of the most important tools in energy engineering. It helps us predict fluid flow, pressure evolution, CO2 plume migration, hydrogen storage behavior, and long-term subsurface risk. However, as our models become larger, more complex, and more uncertain, classical computers are reaching serious computational limits. Today, we will connect 3 important areas: quantum computing, carbon capture and storage, and underground hydrogen storage. The goal is to understand where quantum algorithms may help accelerate reservoir simulation, uncertainty analysis, optimization, and decision-making. This is where qubits meet the subsurface. A trillion-dollar subsurface problem. The subsurface is becoming one of the most important frontiers in the clean energy transition. Every year, the world emits tens of billions of tons of carbon dioxide. To reach carbon neutrality, we must capture and store a significant fraction of these emissions safely underground. At the same time, hydrogen demand is expected to grow strongly because hydrogen can support clean industry, long-duration energy storage, and future energy security. But these systems are extremely complex. CO2 storage requires us to predict plume migration for hundreds or even thousands of years. Underground hydrogen storage requires us to model repeated injection and withdrawal cycles, gas mixing, pressure changes, and possible geochemical or microbial reactions. The capital investment is enormous, and the risks must be carefully managed. This is why advanced simulation is not optional. It is a foundation for safe and economic deployment. In this video, we focus on 3 pillars. The first pillar is CCUS, which stands for carbon capture, utilization, and storage. In CCUS, carbon dioxide is captured from industrial sources and injected into deep geological formations, such as saline aquifers or depleted oil and gas reservoirs. The key challenge is to predict where the CO2 plume will move and whether it will remain securely trapped. The second pillar is hydrogen. Hydrogen is an energy carrier that can help decarbonize sectors that are difficult to electrify, such as steel, chemicals, shipping, and heavy industry. The third pillar is underground hydrogen storage, or UHS. This technology stores hydrogen underground at large scale, allowing seasonal energy buffering. Together, these 3 pillars define a new role for the subsurface in the clean energy future. Let me show you the roadmap for this episode. We will begin by discussing why classical reservoir simulation is becoming increasingly difficult. Then, we will introduce quantum computing in a simple and intuitive way. After that, we will look at several quantum algorithms that may change how we solve reservoir simulation problems. In the second half, we will connect these ideas to real subsurface applications. First, we will discuss CCUS and CO2 plume forecasting. Then, we will examine hydrogen and its unique subsurface behavior. Finally, we will focus on underground hydrogen storage as a cyclic, grid-scale energy storage technology. By the end of this video, you should understand not only what quantum computing is, but also why it may become important for future reservoir simulation, optimization, and uncertainty quantification. Reservoir simulation is essentially a digital twin of the subsurface. We take a geological formation and divide it into many small grid cells. Each cell represents a small part of the reservoir, with properties such as porosity, permeability, pressure, temperature, saturation, and fluid composition. Then, we solve physical equations to predict how fluids move through the porous rock over time. These fluids may include oil, gas, water, CO2, hydrogen, or brine. The simulator helps answer critical questions. Where will the CO2 plume travel? How much hydrogen can we recover? How fast will pressure increase? Where should we place injection or production wells? At the heart of reservoir simulation are mathematical equations. The first major equation is Darcy's law, which describes how fluid flows through porous rock. Flow depends on permeability, viscosity, and pressure gradient. If permeability is high, fluids move more easily. If viscosity is high, flow becomes more difficult. The second equation is mass conservation. This ensures that fluid mass is not magically created or lost. For every grid cell, The simulator tracks how much fluid enters, leaves, accumulates, or is injected. The third equation is reactive transport, which becomes important for CO2 dissolution, mineral trapping, hydrogen reactions, and geochemical changes. The challenge is that these equations are coupled, nonlinear, and must be solved across millions or billions of grid cells and many time steps. This is why reservoir simulation is computationally demanding. Classical reservoir simulation is powerful, but it is hitting a hard ceiling. Modern field-scale models can contain hundreds of millions or even billions of grid cells. Long-term CO2 forecasts may require millions of time steps, especially if we want to evaluate storage behavior over hundreds or thousands of years. In addition, uncertainty quantification requires many realizations. We do not know the exact permeability field, fault properties, caprock strength, or boundary conditions. Therefore, we may need hundreds or thousands of simulations to understand risk. The problem is not only the size of one simulation. The real problem is the combination of large models, long time periods, nonlinear physics, and uncertainty. This creates enormous computational cost. This is one reason why researchers are exploring quantum computing, not to replace every classical simulator immediately, but to accelerate the most difficult parts of the workflow. There are three major bottlenecks in classical reservoir simulation. The first is the curse of dimensionality. When we increase the number of grid cells, components, phases, reactions, or uncertain parameters, the computational burden grows rapidly. Memory and data movement become serious limitations. The second is nonlinear coupling. Reservoir simulators solve pressure, saturation, composition, temperature, and chemistry together. These variables influence each other. For example, pressure changes affect flow, flow changes saturation, saturation changes mobility, and chemistry changes rock-fluid interactions. This requires repeated Newton iterations. The third bottleneck is uncertainty quantification. A single simulation may already be expensive, but robust decision-making requires many simulations. For CCUS and UHS, we need to know not only the most likely outcome, but also the worst-case scenarios. These bottlenecks create an opportunity for new computational paradigms, where probability waves replace floating-point arithmetic. Now we enter the world of quantum computing. Classical computers process information using bits. A classical bit is either 0 or 1. Quantum computers use qubits, which can exist in superposition. This means a qubit can represent a combination of 0 and 1 before measurement. Quantum computing does not simply mean a faster classical computer. It is a different way of processing information. It uses superposition, entanglement, and interference to manipulate probability amplitudes. For reservoir simulation, the hope is that quantum algorithms may accelerate certain mathematical tasks, such as solving large linear systems, optimizing well placement, evaluating complex molecular interactions, or building faster surrogate models. We must be realistic. Quantum computing is not yet ready to replace commercial reservoir simulators, but it may become a powerful co-processor for selected bottlenecks. Let us compare classical bits and qubits. A classical bit can be either 0 or 1. It is like a switch, off or on. To represent many possible states, we need many bits. A qubit is different. It can be represented as a combination of two quantum states, written as alpha times 0 plus beta times 1. This is called superposition. When multiple qubits are combined, the quantum system can encode a very large number of amplitudes. However, this does not mean we can simply read all answers at once. Measurement collapses the quantum state. The power of quantum computing comes from designing algorithms that amplify useful answers and cancel out wrong ones through interference. This is why quantum algorithm design is so important. The hardware alone is not enough. We need algorithms that map reservoir problems into quantum structures efficiently. Today's quantum platforms. There are several types of quantum hardware being developed today. The first is superconducting qubits, used by companies such as IBM, Google, and Rigetti. These systems can have fast gate operations, but they require extremely low temperatures and have limited coherence times. The second is trapped ion quantum computing, used by companies such as IonQ and Quantinuum. Trapped ion systems can have high fidelity and long coherence, but their gates are generally slower. The third is neutral atom quantum computing, developed by groups such as Chu-era, Pascal, and atom computing. Neutral atoms can support large and reconfigurable arrays and are promising for analog and hybrid quantum simulations. For reservoir simulation, the specific hardware matters because different algorithms require different levels of qubit count, gate fidelity, connectivity, and error correction. The field is still evolving rapidly. The era question. Quantum computing today is mostly in the NSQ era, which means noisy intermediate-scale quantum. These devices may have hundreds or thousands of physical qubits, but they are noisy and error-prone. Because of this, today's quantum algorithms often use hybrid methods. A classical computer performs part of the calculation, and a quantum processor performs selected operations, such as evaluating a quantum circuit or kernel. Fault-tolerant quantum computing is the future goal. In that era, quantum error correction will allow reliable long computations. This would unlock more powerful algorithms such as HHL, full quantum phase estimation, and large-scale quantum chemistry. For reservoir simulation, the key message is this. In the near term, quantum computing will likely support hybrid workflows. In the long term, fault-tolerant quantum computers may enable deeper acceleration of simulation and optimization tasks. There are 4 quantum algorithm families that are especially relevant to reservoir simulation. The first is HHL, the Haro-Hasidim-Lloyd algorithm. It is designed for solving linear systems, which are central to pressure solvers and flow equations. The second is VQE, or variational quantum eigensolver. VQE is important for quantum chemistry and may help study mineral reactions, CO2 brine-rock interactions, and hydrogen geochemistry. The third is QAOA, or quantum approximate optimization algorithm. QAOA may help with difficult optimization problems such as well placement, completion design, injection scheduling, and storage operation planning. The fourth is quantum machine learning, or QML. QML may support surrogate modeling, history matching, uncertainty quantification, and fast-forward prediction. Together, these algorithms suggest a future where quantum computing supports different parts of the reservoir simulation workflow. Exponential speedup for pressure solvers. HHL is one of the most famous quantum algorithms for solving linear systems. In reservoir simulation, after discretization, many physical equations become large linear algebra problems. For example, pressure equations often require solving a system of the form A times X equals B. Classical solvers, such as conjugate gradient or multigrid methods, are very powerful, but they can become expensive for extremely large systems. HHL offers theoretical speedup under certain conditions, especially when the matrix is sparse and well-conditioned. In principle, it can scale logarithmically with the system size. However, there are important caveats. The speedup depends on efficient state preparation, matrix properties, condition number, and how we extract useful information from the quantum state. Real reservoir systems are often ill-conditioned, heterogeneous, and strongly coupled. So HHL is promising, but it is not a magic button. It is a potential accelerator for carefully prepared linear systems. NSQ-era workhorses. VQE and QAOA are especially important because they are suitable for near-term quantum devices. VQE is commonly used for quantum chemistry problems. In the context of CCUS, it may help us understand CO2 brine-rock reactions at a molecular level. For example, how does CO2 interact with mineral surfaces? How fast does dissolution occur? How stable are carbonate minerals? These questions are important for long-term mineral trapping and caprock integrity. QAOA is designed for optimization problems. Reservoir engineering has many difficult optimization problems. Where should we place wells? How should we schedule injection rates? How should we configure smart completions? And how should we minimize leakage risk while maximizing storage capacity? In the NSQ era, hybrid variational algorithms like VQE and QAOA may provide practical early applications. They combine classical optimization loops with quantum circuit evaluations, surrogates that replace months of simulation. Quantum machine learning may become one of the most practical early applications for reservoir workflows. Full physics simulation is expensive. If we need thousands of scenarios for uncertainty quantification, history matching, or optimization, running full simulators every time can be too slow. A surrogate model learns the relationship between input parameters and simulation outputs. For example, it may predict CO2 plume extent, reservoir pressure, hydrogen recovery, or fault risk. Quantum machine learning can introduce quantum kernels or quantum feature maps that may capture complex patterns in high-dimensional data. The idea is to train the model on a limited number of full physics simulations and then query it very quickly across many scenarios. For real-time decision support, this could be very powerful. A quantum-enhanced surrogate could help operators evaluate thousands of possibilities faster than conventional simulation alone. Now let us focus on CCUS. CCUS is one of the most important technologies for reducing emissions from industrial sectors that are difficult to decarbonize. The idea is to capture CO2 before it enters the atmosphere, transport it, and inject it into deep geological formations for long-term storage. From a reservoir simulation perspective, CCUS is challenging because CO2 behaves differently from water or oil. It is buoyant, compressible, and strongly affected by capillary forces, relative permeability, dissolution, and geochemical reactions. We also need to simulate very long timescales. Industrial operations may last decades, but storage security must be assessed over hundreds to thousands of years. This creates a computational challenge. We need accurate plume prediction, pressure forecasting, geochemical modeling, uncertainty quantification, and risk analysis. This is where quantum computing may eventually provide acceleration. From megatons to gigatons per year, the scale of CCUS deployment must increase dramatically if it is to contribute meaningfully to climate targets. We are not talking about small laboratory systems. We are talking about industrial-scale injection, large storage complexes, thousands of wells, and monitoring horizons that may extend for centuries. This scale creates several simulation challenges. First, we need to evaluate many possible storage sites. Second, we need to design injection strategies that maximize storage while controlling pressure. Third, we need to assess risks related to leakage, induced seismicity, caprock integrity, and long-term plume migration. Each storage site has geological uncertainty. Therefore, each site requires many simulation scenarios. If CCUS scales globally, the computational demand will grow enormously. Quantum computing may help not because every reservoir simulator will become quantum, but because selected steps, linear solvers, chemistry, optimization, and surrogate modeling may be accelerated. From mechanisms for timescales, CO2 storage security depends on several trapping mechanisms. The first is structural trapping. This occurs when CO2 is physically trapped beneath an impermeable caprock. It is the dominant mechanism in the early stage. The second is residual trapping. As CO2 migrates and brine re-enters the pore space, some CO2 becomes trapped as disconnected droplets. This reduces mobility and increases security. The third is solubility trapping. CO2 dissolves into brine over time. Dissolved CO2 is less buoyant and therefore less likely to migrate upward. The fourth is mineral trapping. Over long timescales, dissolved CO2 can react with minerals and form stable carbonate phases. Each trapping mechanism occurs over a different timescale. This makes simulation difficult because we need to model both short-term injection behavior and long-term geochemical evolution. Quantum chemistry and quantum-enhanced transport modeling may eventually support this task. 3 concrete acceleration targets. For CCUS, quantum computing may contribute in 3 concrete ways. First, HHL or other quantum linear solvers may accelerate the pressure and flow equations that appear inside each time step or Newton iteration. This could be useful for very large models. Second, VQE may support mineral trapping studies. Mineral reactions involve electronic structure problems, and quantum computers are naturally suited for quantum chemistry. This may improve our understanding of CO2 rock reactions, especially under reservoir pressure and temperature. Third, quantum machine learning may accelerate plume forecasting. Instead of running thousands of full physics simulations, we can train a surrogate model and use it for rapid uncertainty quantification. The key point is that quantum computing does not need to replace the entire CCUS simulator. It can target the most expensive modules and work as a specialized accelerator in a hybrid workflow. The molecule that decarbonizes heavy sectors. Hydrogen is increasingly viewed as a key energy carrier for the clean energy transition. It can support sectors that are difficult to electrify directly, such as steel production, ammonia synthesis, refining, shipping, aviation fuels, and high-temperature industrial heat. Hydrogen can also store renewable energy over long periods. However, hydrogen is not an energy source by itself. It must be produced from other energy sources. The climate benefit depends strongly on how the hydrogen is produced. For reservoir simulation, hydrogen introduces new subsurface challenges. It is very light, highly mobile, and can interact with microbes and minerals. Its storage behavior is different from natural gas and very different from CO2. This means that underground hydrogen storage requires dedicated modeling approaches. We need to simulate cyclic injection, withdrawal, gas mixing, pressure changes, and possible loss mechanisms. This makes hydrogen a fascinating and difficult subsurface simulation problem. Production pathways at a glance. Hydrogen is often classified by color, based on how it is produced. Gray hydrogen is produced from natural gas without carbon capture, so it has a high CO2 footprint. Blue hydrogen is also produced from fossil resources, but with carbon capture and storage to reduce emissions. Green hydrogen is produced by electrolysis using renewable electricity, so it can be nearly zero carbon if the electricity is clean. White hydrogen refers to natural geological hydrogen, which is an emerging topic. It may exist naturally in the subsurface, but exploration and production methods are still developing. This slide is important because it connects hydrogen storage to the broader energy system. Underground hydrogen storage becomes especially valuable when hydrogen production varies with renewable energy supply. If we produce large amounts of green hydrogen during periods of surplus electricity, we need a place to store it at large scale. That is where UHS becomes essential. Hydrogen behaves very differently from CO2 underground. Hydrogen has much lower density than CO2. This means buoyancy effects can be strong, and hydrogen may tend to migrate upward if containment is not sufficient. Hydrogen also has low viscosity, which can make it highly mobile in porous media. Its molecular diffusivity is high, so it can spread faster at the molecular scale. Hydrogen can also participate in microbial reactions. Certain microbes may consume hydrogen and produce methane or hydrogen sulfide. This can reduce storage efficiency and affect gas purity. CO2, on the other hand, can dissolve into brine and react with minerals to form carbonates. Hydrogen does not have the same trapping behavior as CO2. Therefore, we cannot simply use CO2 storage models and assume they will work for hydrogen. UHS needs its own physics, chemistry, and simulation framework. Underground hydrogen storage can be understood as a large-scale, long-duration energy storage system. When renewable electricity production is high, hydrogen can be produced and injected underground. When energy demand is high, hydrogen can be withdrawn and used for power generation, heating, industry, or transportation. This is why UHS can be described as a grid-scale battery. However, unlike electrochemical batteries, underground storage can potentially store very large energy volumes over long periods. From a simulation perspective, UHS is challenging because it is cyclic. We are not only injecting once. We repeatedly inject and withdraw hydrogen. This creates cyclic pressure behavior, changes in gas saturation, hysteresis effects, gas mixing, and possible changes in deliverability. To design a UHS project, we need to answer questions such as, how much hydrogen can be stored? How much can be recovered? How fast can it be delivered? How stable is the system after many cycles? Salt caverns, depleted gas fields, and saline aquifers. There are three major underground hydrogen storage options. The first is salt caverns. Salt caverns have excellent sealing properties and can support fast injection and withdrawal cycles. They are already used for gas storage, but they are limited to areas with suitable salt geology. The second option is depleted gas fields. These have known geological structures, existing data, and sometimes existing infrastructure. They can offer large storage capacity, but hydrogen may mix with residual methane or other gases. The third option is saline aquifers. These have the largest theoretical storage potential, but they are also the most uncertain. They require careful assessment of containment, flow behavior, cushion gas, and recovery efficiency. Each storage type involves trade-offs between capacity, cycle rate, purity, cost, and risk. Simulation is essential for comparing these options and identifying which site is suitable for which energy storage purpose. For challenges no other reservoir has. Underground hydrogen storage has several unique physics challenges. The first is microbial activity. Some microbes can consume hydrogen and produce methane or hydrogen sulfide. This can reduce hydrogen recovery and create safety or corrosion concerns. The second is cyclic injection and withdrawal. Repeated cycling changes saturation pathways and may cause hysteresis in relative permeability and capillary trapping. This means storage behavior depends on operational history. The third is cushion gas optimization. Cushion gas is needed to maintain reservoir pressure and deliverability. But cushion gas can be expensive, so the question is, how much cushion gas is enough? The fourth challenge is gas mixing and fingering. Hydrogen is light and mobile, so it may override other gases or form unstable flow patterns. These challenges make UHS a highly dynamic simulation problem. Quantum optimization and quantum machine learning may help accelerate scenario evaluation and operational design. How quantum unlocks cyclic optimization. A possible quantum-enhanced UHS workflow may look like this. First, we generate many geological realizations to represent uncertainty. Then, we run forward simulations or train quantum-enhanced surrogate models. These models can predict pressure, saturation, deliverability, and recovery performance. Next, optimization algorithms, such as QAOA, may help select well locations, cushion gas volumes, injection schedules, and withdrawal strategies. Finally, quantum uncertainty quantification may help evaluate operational risk across many scenarios. The business outcome is clear: better storage capacity, lower cushion gas cost, faster decision loops, and more reliable seasonal energy delivery. Again, the realistic path is hybrid. Classical simulators will remain central, but quantum algorithms may accelerate selected components, especially optimization, surrogate modeling, and uncertainty analysis. For UHS, where cyclic operation creates many possible scenarios, faster simulation and optimization could be highly valuable. Now, we need a reality check. The future is not likely to be purely quantum reservoir simulation, at least not in the near term. A more realistic architecture is hybrid classical quantum computing. Classical high-performance computers are excellent at mesh generation, data handling, visualization, outer Newton loops, and many numerical operations. They will continue to do what they are good at. Quantum processors may act as specialized coprocessors. They may be used for selected linear solves, eigenvalue problems, combinatorial search, or quantum kernel evaluations. This hybrid architecture is important because reservoir simulation is a complex workflow, not a single equation. Some parts are well suited to classical computing, while others may benefit from quantum acceleration. The key message is quantum computing should be used where it provides unique advantage, not everywhere. The realistic path is integration, not replacement. The road from quantum pilot studies to production-scale reservoir simulation will take time. In the near term, we may see proof-of-concept studies on small reservoir problems using hybrid quantum classical workflows. These may involve simplified pressure solvers, small optimization problems, or quantum machine learning surrogates. Later, as quantum hardware improves, we may see larger demonstrations involving logical qubits, improved error correction, and more stable algorithms. Eventually, fault-tolerant quantum systems may support more advanced reservoir simulation modules. However, several open problems remain. State preparation is difficult. Error correction has major overhead. Data input and output can become bottlenecks. Some claimed quantum speedups may be reduced by improved classical algorithms, a process sometimes called dequantization. So the future is exciting, but we must be honest. Quantum reservoir simulation is not ready for full field deployment today. But now is the time to build the methods, workflows, and scientific foundations. Quantum meets the subsurface. Let us close with the main message. Reservoir simulation is becoming more important than ever because the subsurface is central to the clean energy transition. We need simulation for CO2 storage, hydrogen storage, geothermal systems, pressure management, geomechanics, and long-term risk assessment. At the same time, simulation is becoming more computationally demanding. Larger models, longer timescales, more physics, and more uncertainty are pushing classical computing toward its limits. Quantum computing offers a new direction. It may accelerate selected tasks such as linear systems, quantum chemistry, optimization, and machine learning surrogates. The most realistic near-term future is hybrid. Classical HPC handles the full workflow, while quantum processors accelerate specific bottlenecks. Thank you for watching this episode of the Deep Tech series. If this topic opened your mind, please like, subscribe, and follow for the next episode, where we will go deeper into quantum chemistry, catalysis, and clean energy materials.